This is Mr. Anderson for Kellogg Community College. Today we're going to look at the properties of logarithmic functions. This is section 4 of chapter 9 of Math 121 Intermediate Algebra. Well, it would first help us to remember some of the exponential rules. For example, one of the exponential rules is if you have x to the fourth times x cubed, that's going to give you x to the seventh. So multiplying the same bases and the powers get added. Same thing goes if you do the quotient rule here. So if you have x to the seventh divided by x to the fourth, this is going to give you x cubed. Now these two rules are going to be part of our three sets of rules here that we're going to use for logarithms. Since a logarithm is the inverse of an exponential function, the same rules apply since we're dealing with power rules. We're dealing with rules that multiply instead of add. Excuse me. So what we're going to do first is take a look at just the basic rule as written in the book, and I'm going to show you some examples with it. So this is log base A of the product mn. So let's say that inside here you have some kind of monomial that can be broken into, the product of m times n. You can split those apart. Log base A m plus log base A of n. Now that's sometimes useful because what we can sometimes hope is that the base A and one of these m's or n's are going to make this easy to simplify. I'm going to start off with an example here, and I'm going to use this for the next couple problems here. So let's just quickly hammer out that log base 2 of 64 is equal to 6, because 2 to the 6th power is 64. So if I have a problem, let's say for this first example here, that my log base 2 of 4 times 16. If I didn't know to multiply 4 times 16 to make 64, I can use my product rule and take this into log base 2 of 4 plus log base 2 of 16. And then what you get here is 2 what power of 2, or 2 to the what power is 4. You get an answer of 2 here. And 2 to the what power is 16, which is 4. Because 2 to the 4th power is 16, and you can see that 2 plus 4 makes 6. Now the power rule is kind of a nice little shortcut technique. So if I have log base A of m raised to the p power, I can rewrite the problem as p times the log base A of m. So let's kind of talk a little bit about this example here and show you where it seems weird to just take the exponent and move it to the front, but actually we've seen this in a previous video, a problem that could help us with this. So let's take a look first of all at log base 6 of 6 to the 9th power. Now what we did in the previous video is we had a problem where I said, okay, what power of 6 will make 6 to the 9th power? And the obvious answer there was, well, that would be 9. But in this case, what this gives us is a chance to look at this problem as we can break it down. So one way to think of this here is that if we bring the 9 out to the front, we have log base 6 of 6. And if we then ask that question, so what power of 6 gives me, gives me 6, and the answer is 1. So this entire part of the problem turns into 1. So this would give me 9. Now there are other different examples and other ways to look at it, but what I'm going to show you here, that log, or the common log, log base 10 of 10, that's going to be equal to 1. So this is another, inside of this power rule for logarithms, there is another little rule that we'll be looking at the end of this worksheet, that when you have the base equal to what this is of, that's going to be equal to 1. And that's a pretty nice shortcut, as we're going to see at the end of this worksheet. Now the quotient rule is just going to be taking this and subtracting them. because if I start out with the log base a of maybe m divided by n, this is going to give me the log base a m minus log base a n. So I subtract the two of these. And again, this is pretty nice if I have a problem that's set up in fraction form, like let's say log base 2 of 256 divided by 4. I can rewrite this as log base 2 of 256 minus log base 2 of 4. So what is log base 2 of 256? Well, that is going to be 8. And log base 2 of 4 is going to be just 2. And 8 minus 2 is 6. Now go back to our top part of the problem here. You can see that this is log base 2 of 64 is equal to 6. 256 divided by 4 is 64. Alright, so these are little examples using the product rule, using the power rule, and using the quotient rule. Now the rest of this first side of the worksheet here is going to be us to quickly just expand and evaluate these. Now there is a typo. This worksheet here, I accidentally have a 1 there, so please make sure that gets fixed because it should be 32, not 132. Alright, so let's take a look here. Now it says rewrite this as a sum of logarithms. So this is going to be log base 2 of 16 plus log base 2 of 32. Now this is about where the book ends. Now we actually can take this a little bit further because 2 to the what power is 16. That would be 4. And 2 to the what power is 32. That would be 5. So your answer for this problem, completely simplified, is 9. Same thing here. We can take our log base 5 of 25 plus log base 5 of 125. So 5. Now this is where the book might end, but I will push you a little bit forward. 5 to the what power is 25. That would be 2. 5 to the what power is 125, and that would be 3. So your answer is 5 for this problem. Now what we're going to do is combine these together. So in problems 1 and 2 we were breaking them apart. In problems 3 and 4 we're going to put them together into a single logarithm. So this is going to be log base b of 5 times 9, which is 45. And here we have log base t of h and m, which is like that. In problems 5 and 6 we're going to rewrite this equivalent expression that's a product instead of an exponent here. So I'm going to move the 5 out front because we can take the exponent according to our second rule up there, the power rule. We can take this 5 and move it out to the front. So this is 5 log base b of t, and this is going to be negative 5 log base c of m. Okay, moving to 7 and 8, 9 and 10. We're going to be writing these as subtractions, or logs being subtracted, and then we're going to put them back together in 9 and 10. So here, my equivalent is going to be log base 3 of 29 minus log base 3 of 13. Okay, over here we're going to have log base a of y minus log base a of x. Okay, now down here for problem 19, we're going to put these together. So since these are being subtracted, let's write these as a single logarithm. Log base b of 3 over 32, and this is going to be log base a of 26 over 2. Now it is good to note that you may want to check to see if you can simplify any of these. 29 cannot be factored into some base of 3, so it cannot be factored into 27 nor 9, and this can't be factored into anything with 9. Since these are all letters, there's nothing to simplify there, and 32 and 3 are not divisible by 3. 32 is not divisible by 3, so you cannot simplify this. But we can simplify number 10, log base a of 13. Alright, now we're going to go to the second side here. we're going to take this expression 11, 12, 13, and 14, and we're going to split this up. Chemistry students should be used to doing chemical equations and balancing, so this might actually benefit the chemistry students who've just been through lessons where they've had to do a lot of chemical equations. So what we're going to do here is we're going to write an equivalent expression in individual logarithms of w, x, y, and z. So we're going to split this up. Log base a of w. Now since we're going to use the product rule here, we can add then log base a of x plus log base a of y. And now what we're going to do is take this and break it up as well. I'm going to start a little bit over on my left so I can write a little bigger. Log base a of x plus log base a of y squared plus log base a of z to the negative third power. Now you'll note that I wrote my little exponents on the outside of these parentheses because I can take this problem one more step. Because of the power rule, I can take the 2 and the negative 3 and move those up front. So log base a x plus 2 times log base a y minus 3, or plus negative 3 if you're so inclined, log base a of z. Now when we get down to problem number 13 and 14, these problems are going to get rather long, so if you want to use a separate piece of paper, I don't blame you. So this is a quotient. So quotients have to be written as subtraction problems. So this is going to be log base b of w squared x minus log base b of y cubed z. Whoops, there shouldn't be a cube there. Now what I'm going to do is take care of the left-hand side first. I'm going to take this as log base b w squared plus log base b x. Now that 2 can get moved out to the front, so this left-hand side becomes 2 times log base b w plus log base b x. Now here's where you're going to make a mistake, probably. Now when I start to subtract these two values here, you'll notice that I got to break this up. So, I mean, you're just going to kind of use your product rule here. We're going to log base b y cubed plus log base b z. Now here's your mistake that you made. This subtraction is subtracting the whole thing. So if you write your subtraction once, you're actually making a mistake by not writing it here again. So by putting parentheses, this gives you the idea that that subtraction is doing the entire denominator. So this is going to be minus 3 log base b y minus, not plus, because we have to distribute the subtraction sign, log base b z. And I'm sorry, my z's have little lines through them so they don't look like 2's. But that is the final answer to this problem. And most people make a mistake by having this as a plus instead of a minus. Now this next problem is going to take a lot of room, so I am going to clear the screen here, so make sure to pause the video here, copy down anything you need. Okay, there we go. Now what I'm going to do is take maybe this space down here to do my problem. So the first thing I'm going to do, I notice that this is the fourth root, which means that I can rewrite this as the log base a of the quarter power of x to the 8th, y to the 12th, all over a cubed z to the 5th. Now, why did I write it as the fourth power? Any radical, like let's say the fourth root, is equal to that x raised to that fractional fractional power. So it's analogous to say that the cubic root of x is x to the 1/3, and the square root of x is x to the 1/2 power. So let's see how I will write this out. The 1/4 will be brought out in front of log base a. But that 1/4 is going to multiply everything on the inside. I mean, that 1/4 has to be distributed to everything here. So this is going to be 1/4 of x to the 8th y to the 12th over a cubed z to the 5th. Now I'm going to break this into, since this is a quotient, I'm going to break this into two problems being subtracted. So this is 1/4 log base a, and that's going to be, let's see here, I'm going to have x to the 8th y to the 12th minus log base a cubed z to the 5th. Now already I've made a mistake because what I've noticed is that the 1/4 is only multiplied by this part. So what I need to do is put this around nested parentheses, these parentheses, to say that when I get done with this problem, I'm going to probably multiply everything through by 1/4, which is pretty handy because as I break these up here, because this is going to be broken into log base a of x to the 8th plus log base a of y to the 12th. The 8 and the 12 are both divisible by 4. Things get a little more complicated over here. This is log base a of a cubed. And then we have log base a of z to the 5th. Now again, what's tough about this is you'll notice that this is subtracting, so it technically has to subtract both of these. So now you see that I have a lot of parentheses here just to deal with my 1/4 out in front. Well, let's go try to take care of business here. What I have here is that 8's going to have to get moved to the front. So this is going to be 8 log base a of x plus 12 log base a of y. Put little parentheses around those. Minus 3. Now log base a of a is just 1. So this simplifies to 1 times 3, so just the 3. And I'm going to distribute the minus there, so that's going to be a minus. Bring the 5 out in front, and log base a to the z power, this is just going to be log base a of z. I said to the z power, I didn't mean that. Alright. Now everything has to get multiplied by 1/4, which is going to simplify things a little bit. That's going to be 2 log base a to the x, or of the x, sorry, of x. Sorry. 1/4 of 12 is 3 log base a of y. 1/4 and 3 just makes 3/4. And 1/4 and 5 just makes 5/4 log base a of z. Whew! That was a lot of work, but luckily the rest of this worksheet isn't going to go as long as that problem did. Okay, let's look at problem 15. Problem 15 is going to put this into a single expression, and in doing so, we will actually be reviewing some old rules of algebra, because you'll notice that these two are being subtracted, which means that inside of log base a, I'm going to have the fraction of a over the square root of x divided by the square root of ax. And that right there is kind of hard to process. So dividing fractions, please don't cry. Skip, flip, and multiply. So remembering a little algebra trick from earlier, instead of writing this as a over x divided by the square root of ax, we're going to write it as this. We're going to write it as a over square root of x times 1 over square root of ax. Since these are both radicals of the same root, we can combine those together. We can go log base a times 1 is a, and then x times ax is the square root of ax squared. Now if you go look in the back of the book, you'll notice that that's not the answer. And it's because we have a square root in the denominator. Let's get that square root out of the denominator by multiplying the top and bottom by the square root of a. Now the reason why I chose the square root of a is because if I multiply the top and bottom by square root of a, what this will give me in the numerator, well, it'll give me a square root of a, but in the denominator it will give me the square root of a squared x squared, which can be taken out of that radical. So the log base a of this problem then converts to, let me move up here to get some more room, log base a of a square roots of a over ax. And then one more simplification step. We're going to notice that the a is in the numerator and denominator, so this is log base a of the square root of ax. It is also possible you could have rationalized this denominator here and could have gotten your problem to look a little bit different at the beginning, but it would get you to the same answer. So if we're looking at problem 16, we're going to combine this into another quotient. So this is going to be, let me just put a little line here so we know these are separate. Log base a of, now since this is a quotient, we're going to put these above each other. 2x plus 10 divided by x squared minus 25. But these are factorable. In fact, the numerator can be factored as well as the denominator. The numerator we can factor out of 2, x plus 10, or x plus 5, whoops, edit, huh? Alright, so 2x plus 5, sorry about the little mess there, and that's over, this is a difference of squares, x plus 5, x minus 5. So the x plus 5's cancel out, or simplified is to 1, and so log base a of 2 over x minus 5. Now our last four problems are probably some of the shorter ones here. So here what we have is we're given that log b is equal to this equation. Log b is equal to the 0.792. Now we don't know what the base of b is, but we're just kind of going on the flow that if we can turn our problem into some form of log b to the third power, or no, log b of 3, we can get this decimal. So let's go and see how we can do that with problem number 17. So we have to think to ourselves here, how can I take 1/3 to the what power would give me 3? So 1/3 to the what power will flip it on its head? And the answer to that is -1. 1/3 raised to the -1 power flips this reciprocal and makes it 3 over 1, or just 3. So if I change this problem to log base b of 1/3 raised to the -1 power, I can then change it into this. So what this becomes is that this 1/3 changes to a 3, and it gets rewritten like that. I don't have an eraser here, so I have to overwrite here. And that brings my -1 out in front times my log base b of 3, which means I'm going to have a -1 times 0.792, because log base b3 is 0.792, and that's going to give me a total of -0.792, or -792 thousandths. Now in problem 18, what you will do is you'll split this up, because this is a product, so we'll use the product rule. So this gives me log base b3, oh good, we need that, plus log base b of b. Well, log base b of b is 1, and log base b of 3 is that decimal, 0.792, so our answer here is 1.792, or 1 and 792 thousandths. Now our final answer here is to apply what we learned right here. When you have the base of itself, it simplifies to 1. So this is t times 1, which is t, because base q of q is 1. Or over here, the answer is, like as simple as number 19, -5, because base p of p is 1, and -5 times 1 is -5. Well, thank you for watching.